Yeah, I think.
And then we have wine. It's definitely you should know that. Don't rush.
According to.
Yes. So this is not the last thing of the day.
The most important thing is.
Sorry. After there's the wine reception, so it's amount of 44 minutes after your talk. So.
Oh.
We have time. Come on. If it's more than an hour, we want to learn. If it's interesting, you can.
Yeah, thanks very much for this introduction.
Thank you very much for doing
And I have to warn you in advance, it's not going to be very sophisticated. Oh, good point.
Thank you. I knew. Okay. So think of it as an amateur's introduction into the topic. So there are people who are much more expert here, even in the audience. So I feel a bit embarrassed, but I have to say I'm sorry you have to endure this. Yeah, I already managed to at least. Yeah. No. Well, I told already Francis that he can skip this, and I was successful. So, otherwise I feel I have to tell much more than needed. So I'll start from the very basics and will not go much beyond, as Bruno has asked me to do so. So, and to start with the multiple zetas, let's first revisit the single zetas, which are so-called Riemann zeta values, which are often abbreviated as RZV. And, well, that means we evaluate the famous Riemann zeta function at special points, particularly at integer points. And then we call it a value for some strange reason. And it certainly was already known to Euler much earlier than Riemann. And let me try to indicate why one should expect such a function to have any information on, say, the integers to keep or to.
What was known to Euler?
Euler already knew about Riemann zeta function. So Riemann was, it's very strange to call it after he already knew about it, at least in a certain kind of context. What he didn't know is
there's a functional equation, and
he knew the analytic continuation. He knew. Well, to an extent, yeah. In the way he knew already about negative zetas, so he knew how to regularize in a sense. So, but Riemann actually used it and later on viewed it as a kind of a complex function, and that's not exactly what.
The integer points are known.
Yeah, Euler already knew what they were at integer points, so we'll come to that. So we'll you already know too much. You've even written a paper on zeta value, so I'll be very happy to have someone correct me often enough. So, okay, we'll see. So let's try now a fake motivation. Why should one look at this zeta function? I mean, it's an analytic object. Why should we have that in algebraic context at all? So it seems a bit odd to keep information about the integers. So, as an analogy, think of, for a sequence, say, of real numbers, x1 to xr, finite sequence of positive real, say real numbers. It's often enough to know x1, so the sum of all these, the sum of their squares, up to a certain power, say often power r maybe should be good enough, it's r to the r. If we know those kind of momenta, let's think of those as maybe generalized sort of a higher moments of that set x1 to xr, then we can retrieve. So let's say, if we know those sums and power sums, then can retrieve back these xi themselves.
Up to permutation.
Yeah. Now, well, it's a set, so. 1, 0, 8. Okay. Well, no. Okay. Famous story. You may have heard of Gabber, who is extremely bright and quick. And Jean-Pierre Serre once played that. He prepared in advance his talks very carefully, and he made sure that he looked through that everything was in good shape. And at one point he stumbled and thought, that's something Gabber will notice. So make sure that I'll do it right. And sure as hell, when he gave the talk, Gabber said, here is the talk, here's the problem. And Serre's like, but, you know, blah, 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 blah. And he explained, okay. And then Jean-Pierre Serre wrote down, see, 1 and Gabber 0. Now, the punchline is, at the end of the talk, the score was 1-3. So I'm already at a disadvantage. So I think I'll stop that game soon. Okay, yeah, I need that space anyway for more important information. Okay, so let's try to try this for the infinite sequence. 1, 2, 3, so on. So the integers, positive integers. What do we see here? So suppose we know sum of all the integers, they call it n. They're squares, square sums, and so on. In general, can we say anything about the do these how do I write that? Yeah, these should carry all the information, maybe information about the integers, positive integers, say. So that's a big question mark. So that's a very vaguely phrased statement. So how can we make sense of these? First of all, these don't even converge, so what's the point? Yeah.
Thank you.
Okay, good. So the urge was all. Now comes in our friend Euler, and he knew how to deal with divergent numbers, divergent series, and in particular those beautifully divergent series, easy to handle for him. But at least to end up my motivation, we could be led to study the following function, call it zeta of s, for a strange reason. So sum n, okay, I'll call it n to the minus s for all so s in the negative integers. Then we would have this situation, these momenta, high momenta. Actually, why not all s in z? Even why not all s in c? So we overdo we shoot over the original problem, and then we even try to study that function for any s. So that's sort of my fake motivation why to look at this function at all, and why we might expect that it says something sensible about the integers. Okay, and it turns out that it indeed has a lot of information on z. In fact, it even has or carries information on the multiplicative building blocks. Meaning, of course, the primes. Why that? So first of all, this converges certainly for a real part of s greater 1. It's not a big deal. But then if we go to the limit, where the real part equals 1, we already can get some nice information out of it. So if we write this as a product, that was Euler, the Euler product, as 1 over 1 minus p to the minus s, say, where p runs over all the primes. Then we go from additive to multiplicative, in a sense, breaking it up. And now, when s goes to 1, we read off that on the left-hand side, we get the divergent series, the harmonic sum. And on the right-hand side, well, that can't be a finite sum of products. If s equals 1, it just would be a finite product of those, and it can't diverge. So right-hand side must contain, there's not a rigorous proof, obviously, but must contain infinitely many primes. So that's one thing that that was Euler's proof of the famous Euclid theorem, that there are infinitely many primes. But then we can also read off, with quite some more effort, a far deeper statement in number theory, which is also S, the real part of S equals 1 implies that zeta of S has no zeros. And that was proven by Hadamard, and in the same year by de la Vallée-Poussin with 1898 rather. Yeah, it didn't take that long. So, and that proves the prime number theorem. Meaning that the number of primes below a given x, so p prime, is asymptotically behaves like log x divided by log x. So we get information on the primes here. In that equation also, where when I wrote sum equal to the product, then important theorem goes enters, which is the fundamental theorem of arithmetic, the unique factorization of integers into primes. So we see a number of instances of arithmetic nature already in Zeta, in the Riemann Zeta world. But there is further arithmetic significance. Oops. Oh, yeah. Of those values. And now we get to the analytic continuation of zeta of S gives to almost all values. So we have to take out the point 1 where zeta has a pole, but it's a simple pole and one knows the residue, which is 1. So it's reasonably well behaved there. So when we get the values that values at negative integers, more precisely, already Euler showed that zeta of 1 minus n is minus bn over n. So for n, say greater or equal to 1. And bn is the famous Bernoulli number, nth Bernoulli, which arises as, well, if we take the difference quotient of the function e to the t at the point 0 and take its inverse, then this is the nth coefficient, the coefficient of t to the n in that expansion.
T to the n over factorial.
Yes. Okay, one more. I'm glad you didn't mention the sign for B1. Okay. No, that was prepared. Okay. Yeah, and these Bernoulli numbers occur in many arithmetic contexts, obviously, or I'm sure, and also in algebraic topology. For instance, Hirzebruch's work on what is some of the topological genera, so like L genus of certain oriented manifolds, smooth, some good manifolds of dimension 4 times n, I think. And they occur there. And in Milnor-Kervère invariants,
number of exotic spheres.
also what's called Harris-Siegel summand in algebraic K-theory, or in K-theory then. And I think even Quillen found these Bernoulli numbers pop up in the stable homotopic groups of spheres context. So you should be interested in those. You've seen? Okay. So the strange thing is that there is a lack of patterns, mostly, for these even ones, B to n, and yet they're often what I would call recognizable. What do we mean by that? So the first, so they have big primes relative to the index in their denominator, in their numerators, sorry. Not in their numerators, sometimes. So sometimes you can have.
Okay, no.
Mm-hmm. Is that a point for me? No?
Not 1 point.
No. Okay, the most famous one being for B12, which is up to sine 691 divided by 2730. So this is a prime. And so 691 compared to 12 is pretty big. So whenever you find something true up to 691 or a multiple of 691, you should stop and look for the Bernoullis. It's really so telling, it's amazing. Okay, now every odd Bn at least for n greater 1, vanishes. So you would think that doesn't tell you anything, but it does. So instead what it says is, gives the information that certain algebraic K groups of Z have non-trivial rank. And they also helped Euler solving a famous problem by the Bernoullis. So they asked, what is, well, the sum of the inverse squares? And I know everybody among you will know it. You're not allowed. Square root of 6. And in general, sum 1 over n to the 2k is known to be pi to the 2k times multiple, which has to do with the 2kth Bernoulli number. And then you divide by 2k factorial and some power of 2 and plus or minus sign, whatever. So Euler already knew that. And as an upshot, we know that zeta 2n are all, so for n greater 0, obviously, algebraically independent over Q.
No. Algebraically dependent. Zeta 2n.
Zeta 2n. They're algebraically. Sorry.
They are powers of pi.
Yeah, sorry. Yeah.
Linearly.
Yeah. Mm-hmm. But we don't know anything about zeta odds. Or, that is, we know a little bit. Two famous results. The first one in 78 by Apéry, that zeta 3 is not rational. That was a big story at the time. And the other one in 2000 by Rivoal, who says that, shown that there are infinitely many linearly independent values, Q linearly independent, of course, among the odd zetas, among zeta 2n plus 1, where n is a natural number. And that's pretty much, I think, the state of the art. But one expects far more.
There's also the striking is zeta 5, zeta 7, zeta 9, zeta 11.
There is
One of them is
at least one of them.
Rivoal.
Yeah, Rivoal and Zudelin, a few years later, had this very strange result. Oh, sorry. So that you take a set of 4, of the first 4 zeta odds, which we don't know, and we know at least that there is one of them that must be irrational. So it's a rather, well, philosophical statement maybe, rather than a real. It's rather strange. But amazing that you can show something like that, obviously. And the folklore conjecture that one has, that the numbers 1, zeta 3, zeta 5. Well, first of all, we expect those to be all algebraically, to be independent. But in fact, even if we divide by the corresponding powers of pi, which seems to be natural after seeing that zeta 2n is a multiple of pi to the 2n, then even those are ... are certainly linearly independent over Q, but I think also algebraically independent over Q. So one hopes far, far more. We don't even know about irrationality of very many of those, but so you see the big gap.
Stronger that if you connect pi, zeta 3, zeta 5, zeta 7, they are algebraically independent, slightly stronger.
Mm-hmm. Okay, well, quarter point maybe for you. Okay, good. That is.
So the next one is zeta 9 or zeta 11? Is it odd prime?
No, it's zeta 9. Good question. Zeta 9. Yes, so the zeta odds. Yeah. Okay, and Euler already tried to find zeta 3 over pi cubed and check that it's not a simple multiple, rational number. By simple, I mean a small denominator. So he computed 10 digits of these numbers, took the quotient, probably continued fraction, and then figured out, well, nothing really striking. It doesn't look rational at all. And yeah, you can do that now with computer algebra systems with thousands of decimals, and it still doesn't look very rational. So, and instead, he tried another approach. As he often did by varying the argument, he now introduced a second one. So to zeta 3. Look at double sums. Okay, let's have a quick look at double sums. So if we just take the product of zetas, we would just sum independently over the summation indices. But here, what he suggested is sum over a cone. So take this as a definition, 1 over m to the a, 1 over n to the b. So where we have this condition on the summation indices. So we have to make sure that, which one is that? Say b is a greater 1. Otherwise there's, this way around it's too fast. So here we have potentially a harmonic sum if we take b equals 1, and that will trigger the whole thing to be divergent. So we force b to be greater than 1. Yeah. Okay. And he asked, can they tell us more about single zeta, so Riemann zeta values? And I think, well, I won't get to that point, I'm sure, but in principle, one of the upshots that I would like to get to is, it seems indeed that they can tell us something. Okay, first surprise, already found by Euler. If you look at zeta 2, 1, it's closely related to...
Sorry, I'm confused. It's A that should be...
No, you should interchange A and B.
Ah! Yeah. Thank you. Okay. So you were right after all.
To interrupt you.
No, you did, but then you didn't insist. Yes. Yeah, so this is the one that will go to a harmonic series. Thank you. Yeah, and so already Euler found that zeta 2, 1 and zeta 3 are closely related. In fact, showed that they're equal. And one even knows that I think there are about 32 variations on the proof. And I think it's called Goldbach variations. Because it appeared in a letter to Goldbach, and I think Borwein, Bailey, I forgot exactly the author, sorry. I think Borwein and collaborators gave a collection of proofs of that statement. And Euler also gave a sum formula. So for instance, take all the zetas, all the convergent zetas, let me be brief, of the following type, A, and call it W minus A for reasons you'll see in a few minutes. That's the same as zeta of W itself. Right, so here you take the double zetas, zeta A, B, but the sum of the two is the same as the W here on the right, and we sum over all of these. So it's a nice sort of distribution of zeta W into the double zeta world. And moreover, if W, or if say A plus B is odd, I think it's, then so A plus B. Then zeta of A plus B is not new. Can be written as sum of products of Riemann zetas. Of two Riemann zetas is enough. So kind of yes?
Do you mean A comma B?
So if A plus B is, thank you, very good. So the double zetas can be reduced if the sum is sort of odd. And if you have three arguments, you know how to do that. Then if the sum is even, you can also reduce it to previous case. But I'll probably not touch on that. Okay, so maybe just to give an impression, like zeta 5, 2, I tried to figure that one out, is 5 times the product zeta 2 times zeta 5, 2 times the product zeta 3 times zeta 4, minus 11 times zeta of the sum of the two. That's one of these reductions that you can example, just to make it a bit more concrete. Okay, so these are the double zeta values. And let me now come to, this is pretty much 18th century methods or results. Now the Renaissance occurred roughly in the late 80s. And I'll mention a few names. I think one, maybe in collaboration or in discussions, they resurrected those numbers, Zaghi and Goncharov. And they also discussed with Grinfeld and Kantsevich, seem to have quite some interest in those numbers. So that's sort of the arithmetic context. Then there was independently, funnily, Hoffman. I would call that more the algebraic context. And roughly at the same time also Broadhurst had found first instances of these double zetas. That was in, say, particle physics. And I guess others also were involved, but these are the ones that I happen to know of in particular. Okay, and by contrast with the previous case, we have many relations. So Euler already gave quite a number of them, but let's try to indicate two types of reasonably simple looking families. So, two families of such relations. The first one being rather obvious. So you will see that in a second. So zeta of AB plus zeta BA plus zeta of the sum of these is simply the product zeta A times zeta B. And this can even prove. So here the sum is, say, over m greater than n. Here is the sum of the same term, in sense, of m smaller n. We've swapped those. And here we have the sum m equals n. So that means if you look at the lower triangle, so below the diagonal, the upper one, and the diagonal itself, that should add up to the independent sum over m and n. And that's essentially what the proof is. And you can even imagine how that generalizes.
And that was already Euler's proof.
I haven't seen that in Euler.
Exactly this.
Okay, you get an extra point. Thank you. So Euler.
Not only he stated it, but he gave exactly that proof.
Mm-hmm. Okay, and another one, which is proved, say, using partial fractions, for instance. Oops. So here we take binomial coefficients times zeta of, that is, r and, say, a plus b minus r. That's also sum of zeta a and zeta b. So here the sum goes from, I think, 2 to a plus b minus 1. So some such formula. So here you have the sum over the double zetas with coefficients. Before, coefficients were pretty much always 1. But that also sums up to zeta a times zeta b.
And the proof is complete by you.
Also by Euler?
It's complete before that standard proof, which is not the one we used to make.
Uh-huh.
Doesn't have a simple combinatorial explanation?
Too difficult. No, not really.
Not like
No. That's not it. I believe that.
Well, what you can do is you look at 1 over m to the a and to the b, and for instance use the partial fraction expansion of this,
Yes, that's okay.
and then you sum up.
That's
That's essentially. Okay. So now one of the features that are in all these equations or identities is that if you look at the indices, or rather the arguments, and think that this has has a kind of weight a plus b, and here r plus a plus b minus r, they are all the same. So all zeta expressions have the same weight, which is a for zeta a and a plus b for zeta a comma b. And it's sort of, it adds up, so, and weight of zeta a times zeta b is a plus b. So it's sort of logarithmic. Okay, and then we have another folklore conjecture that all the expressions, so in short, zeta values of different weight are linearly independent. Yeah, that's maybe not a good way to say. It's weaker than what I actually want to say. So, in fact, all relations can reduce all relations to homogeneous weight. right? If we have a complicated equation, then we just cut it into weight-graded pieces according to that, and then we prove that independently. Oops. Ah. I missed some. Okay. Okay. What is so we reduce to a fixed weight, and now so it's clear. MZV definition is now clear, right? Zeta of K1 up to KD is simply the sum, well, N1 greater ND to 0 of 1 over N1 to the K1 up to ND to KD. And this D is the depth of that zeta value, and the sum of these indices as before is the weight. So these are conventions that one uses. And then the relations above generalize. So the first one is a bit complicated to state without using a good notation, which I didn't want to introduce, so I got stuck sort of. So it's the sum over all shuffles of that sequence A, so which I write as A underscore, and B underscore, which is the sequence of the B's, where contractions are allowed. And contractions are whenever an A is left of some B, then we can add those, instead of two arguments, replace it by a single argument with the AJ plus AI plus BJ corresponding one. So let me do that in one example, then I think you've understood the whole thing.
Can you complete the equation?
Say again, sorry?
Can you complete the equation?
Oh, it's the sum of zeta of sort of the
shuffle.
sequence of the shuffle. Yeah, so maybe sigma shuffle and then sigma of A and B. But this sort of the contracted shuffle. Okay, so I guess that was maybe not completely. So let's do it like zeta 2, 3 times zeta 7, 5. Bruno wanted to be very explicit, wanted me to be explicit, right? So, okay. Okay, what are the corresponding zetas that occur? So there are 6 of those with 2s and 3s and really shuffled. So maybe I'll do it like 2, 3, 2, 3, and 2, 3, 2, 3, and 2, 3. And then you just fill up the 5 7s. Maybe I can even use the colored chalk. Okay. So 7, 5, but it has to be in the same order. So shuffle means it preserves the order of the individual sequences. So 7, 5, 7, 5. I drop the commas. 7, 5, 7, 5, 7, 5. So these are sort of the easy terms. Then a bit more complicated are the ones where there are also 6, unfortunately, of the type where you add 2 adjacent ones. So yeah, let's do it maybe from here. There is an A next to a B, so here's 3 plus 7, 5. There's no other one. So here there's an A next to a B, so we're allowed to plus 7 and leave the rest in place. And we're also allowed to have 3 plus 5 here. And so you keep going, you get 6 such terms. And the last one is one term where you contract even 2 of those. You can contract the minimum of R and S many. So up to that point. So plus zeta, so that would be 2 plus 7 and 3 plus 5. And I checked last night numerically, it really seems to work. So I haven't given you the 3 plus 3 more. But that's a nice.
All possible contractions.
All possible contractions, yeah. And here also the single contractions. Yeah, maybe one. No, I think I've given essentially the idea for all 3 types of contractions here. Okay, but also 2 generalizes. And for that, it's very useful to take a different point of view. And that has been taken by Kancevich. So it seems to have been an innocuous remark. So what I heard, maybe it's an urban legend, but at the time when it was in the early 90s, he was flying around quite a bit, and so did Don Zagier. And they met at an airport, and they got into chatting. Eventually, Kancevich told Zagier, actually, you know, these strange sums that you gave me recently to play around with, they actually can be written as an integral like that. And then a few seconds later, Zagier said, you've proved the conjecture on inversion relation. So there was a famous relation at the time, which wasn't known how to be proven, but by taking that point of view, immediately it popped up. So without knowing, Kancevich proved the inversion relation. So he says zeta of, do I really do that for? Let me do that for double zeta, and then you get the idea. So that's you take variables. So now I'm 1 greater t1 greater t2 greater up to, you need m plus n variables, and you take simplex integral, right? This defines you simplex, so it's an n plus n-fold integral, despite this being just a single one. And then you take dt1 over t1, wedge, dt2 over t2, up to the second to last, so before the m, so it's dt m minus 1 over t m minus 1. And then at tm, things are slightly different. It's 1 minus that whole thing. And then it keeps going. So you start with dt m plus 1 over t m plus 1. And the last one again is, now I count, dt m plus n over 1 minus t m plus n. So that integral represents that zeta value. And it looks even more horrible, but actually is useful because you can now identify since the domain over which you integrate is always the same, you just say, okay, I'll just carry along, that's like 0, it's dt over t minus 0, so that corresponds to 0, that corresponds to that still corresponds to 0, but that corresponds to 1. And similarly, so we can express it in terms of a sequence of zeros and ones, and that will encode our double zetas, and in general, it's clear how to do that for the multiple zetas. So, zeta of mn now gets identified with what we write zeta 0 to the n minus 1, 1, 0 to the n minus 1, 1. And now the shuffle relation for iterated integrals that I'm sure many of you are very familiar with work beautifully. So for example, so essentially what you're doing is you take the product over 2 simplices, the integration domain of this, you multiply zeta, such a zeta value by another one. The product of these integration domains get, well, the integrand gets shuffled as usual, but the domain gets decomposed, gets triangulated into simplices again. And so each simplex itself gives rise to a zeta value, and so you find out that.
What's the notation, right?
So this is sort of a notation, like a new notation for this one, because that corresponds to form dt over t, and the one corresponds to form dt over 1 minus t. And so once you know that sequence of zeros and ones, you can immediately identify it with that iterate integral in this form, right? You write down the zero for each zero, and that's a way to encode zeta mn in terms of zeros and ones. Very useful because there you can see the shuffle immediately. While on m and n, it really looks horrible. So for example, then shuffle relation is, say, m1 up to mr, shuffled zeta of n1 up to ns somehow here, is, if we call that, let me call that as the word m1 minus 1, 1 up to 0 mr minus 1, 1, shuffle the corresponding thing here. And I call that maybe w and this word for word and w prime. Then this is the sum over all shuffles, real shuffles, not contracted shuffles, shuffles of w and w prime in the usual sense, order preserving each of the individual entries in each sequence, zeta of that, I call it sigma, sigma of w prime, with coefficient 1. And maybe I don't have to do that in an example because so if I can recommend, maybe we'll do that as kind of mini exercise here, zeta 2 times zeta 2. That's simple enough. There's just 6 terms, so then you can do that almost in your head, I think.
So is the second equation is just finding the product of the simplest shuffle.
Yes, exactly.
And the first, but then what happens with the contracted shuffles?
Yeah, that's strange because there are sums involved, not integrals.
No, but there's also an integral representation, which I found and which is being developed by my student Sude. So you represent it as an integral, but then you instead of manipulating the domain of integration, the product of two simplicities, to split it into simplicity, you have one domain of integration, which is a cube. We have a cubic integral, a cube by a cube is another cube, but you manipulate the function that you integrate. That's one way. I'm quite sure.
Okay.
The first time I saw this, we was giving ideas to this fields method as well. I mean, this idea does not seem that complicated to write the multiple zeta value in terms of integration.
Yeah.
Nobody discovered that before?
No. It took someone with an eye for both, and it's obvious.
Isn't it true that Leibniz knew it for a single thing? I think he knew that zeta is...
No, he knew that. No, he doesn't represent it as an integral. As far as
He certainly didn't write it as zeta. But I mean, I know the story that Bernoulli wrote to Leibniz and said, what do you know about the following integral, I think about this sum, z to the n over n squared. And then Leibniz wrote it, well, you can write it as this integral dt over t over dt.
But only for 2.
But only for 2.
Only for 2.
So in that sense, he already had this identification. Yeah, and that's maybe why Gontchev and Manin in their paper write
people usually refer to
Leibniz Kontsevich, which is a strange collaboration. Okay, so the set of these relations, 1 and 2, in the general case, are quite rich, but not sufficient to give all. So we'd like to have a system of equations which give us a complete set of relations among multiple zetas. One of the big questions, can we find the algebra that really defines multiple zeta values? And the first blatant example is zeta 2,1 equals zeta 3. That does not follow from anywhere here. So the clever idea that several people had, I'm sure certainly Hoffman, I guess Zagier as well, is to introduce divergent zetas in particular zeta 1. Just take it as a formal symbol, but then how should things behave if we included that? So, whole story. And then do what physicists do. Then once you have encountered these bad terms, well, cancel them if they occur in different ways, right? Two divergences, they look the same. Okay, take the difference. Well, I say appropriate differences. Yeah, let's do it for zeta 1, and I call that shuffle with I write it as a star shuffle, or shuffle seems to have been created by the name shuffle by David Broadhurst. He said shuffle and stuff, and then he put that together he contracted that expression into a contracted shuffle, so it's shuffle. But the word stuffle.
Shuffle was invented by
But we were about stuffle. We were stuffling. So Broadhurst stuffled and shuffled. Yeah, shuffled were certainly in the program long ago. And then we also have zeta 1 shuffle. Zeta 2. Okay, let me. So what do we have here? The stuffle simply gives us zeta 1 2 plus zeta 2 1 plus zeta 2 plus 1. But here we get zeta 1 shuffled with zeta 0 1. Zeta 2 is 0 1 in this different notation. And this now gives us zeta 1 0 1 plus zeta 0 1 1 plus again 0 0 1 1. So the 1 here occurs in 3 different places. And this now is zeta 1 comma 2. This is zeta 2 comma 1 twice. So if we now take the difference, we find that the bad terms zeta 1 2 cancel. These are the divergent ones, and there's one zeta 2 1 left. But here it's twice, so we cancel one of them and are left with zeta 3 equals zeta 2 1. That's one.
It's exactly the proof Euler gave.
So I'm still doing 18th century mathematics. So.
Can you say a few words about this shuffle thing? Because so far it's a definition, not
it's okay. The upshot is it defines a multiplication on multiple zeta values.
Yes.
That's one thing, right? But in fact, there are two. Now, since you mentioned the shuffle and multiple zetas before, I want to point it to you that it's not enough. Shuffle alone is a bit poor. You need double shuffle to make really multiple zeta. And since you have the connection to multiple zetas, so there must be a shuffle somewhere in the context.
Sorry, how could you make the difference? You knew from the start there was an equality on the left, or I didn't get the reasoning.
So now you take the differences of this one minus that. So zeta 1 star, zeta 2, minus zeta 1 shuffle, zeta 2, and that gives you a valid relation among multiple zetas. That's the upshot. Right?
I think the point is that zeta 1 star zeta 2 is equal to zeta 1
Yes.
times zeta
Yes.
2.
It's just a different way. So there are two
formulas
Yes.
for the product.
Even if zeta 1 doesn't really make sense.
You take a formal variable and
No.
oh, no. Yeah, and so we've encountered at least one candidate for a complete set of relations among multiple zeta values. So the upshot, yeah. So a candidate, conjecturally complete set of relations among MZVs by taking 1, that's shuffle, and the third type where we take differences of divergent ones. So these are sometimes called Hoffman relations. So that essentially is zeta of 1 star zeta on index A minus zeta of 1 shuffle, the same index, zeta A. This is 0.
But all the divergences disappear when you make the difference.
Exactly. So that's the surprising thing. Okay, so this is one set. Now, I wanted to have more sets, but beginning to run out of time. Don't know how long I will run out of time. I started late. Oh, you want to go Russian? I mean, Russian style seminar? Oh.
No, I mean,
You have 3 more hours. You have 3 more hours.
3 more hours. Thank you.
Stop when the wine reception.
The wine reception. Come on. You have to.
45 more minutes.
Okay, I'll be very slow. Okay. So that gives a. So since we have all these relations, you get drastic reduction as opposed to just taking formal symbols about, for each multiple zeta. If we take the span of all multiple zetas, divide by all these relations, you get a reduction of dimension of the span which Zagier, I think, has called ZK, is the Q span of all the multiple zetas, say A1 up to AR, where they sum up to K. So this K, which is the weight, maybe I should call it W as before, and A1 equal to 2, and all the others are greater equal to 1. Oops. So that one would like to know the dimension of this space in order to get an idea. I'm just to give you a glimpse, so how it looks like. 6, 7, 8, maybe good enough. Then the dimension. How does it develop?
These are conjectured, right?
Yes, I'll try to get to that conjecture, but develop it, motivate a bit. So here we have zeta 2. So conjectural basis is given by zeta 2 here, and weight 2, right? There's nothing else. Zeta 1, 1 is divergent. Here we have 2 possibilities, zeta 3 and zeta 2, 1, but we know they're related. So it's only a single one, and we can take zeta 3 as one generator. Zeta 4, well, similar. We can show that zeta 4, zeta 3, 1, and zeta 2, 2 are all rationally related. Just get a single one. At 5, we get first time we get a 2, so zeta 5 and zeta, say 2, 3. Yeah, for instance. Well, it doesn't matter. You could even take a zeta 2, zeta 2 times zeta 3, which would make it more convenient. Okay, for here we get 3 and we get 4. No, I think that's not true. No, for 6 is only 2. We have zeta 6 and zeta 3 squared, which are certainly not, well, we don't know it, but we strongly believe that they're not rationally related. Here is a 3, and here is a 4. So here, for instance, zeta 7, zeta 5 times zeta 2, and zeta 3 times zeta 4. These are certainly not related. And then here, for the first time, we get something that's not reducible. So here, maybe that's why I should have stated that as zeta 2 times zeta 3, show that as a product of zetas. But here, zeta 3, 5, or alternatively zeta 2, 6, or the mirror images can be taken as something new. At least conjecturally. Yeah, conjecturally, this is a number which is certainly transcendental, but we can even prove irrationality, of course. That should be a new generator of the, which is not contained in what the Riemann zeta will give.
Not contained in the previous ones.
And not contained in what you can form from taking products of Riemann zetas.
Yeah, okay.
Right? So there's the subalgebra of Riemann zetas in product, but this should not be in that subalgebra. That's the And so the question is, yeah, it grows rather moderately. And, well, if I gave you a few more of those, some of you, I'm sure, would recognize the sequence. So it gave rise to the dimension conjecture. Which is, okay, the dimension of zk is simply the coefficient of t to the k in this quaint little rational expression. 1 over 1 minus t squared minus t cubed. And in other words, recursion, if we call that d sub k, we have dk equals dk minus 2 plus dk minus 3, and that's certainly the one that you had in mind when you asked about this conjecture. And there is actually a theorem about this due to Goncharov, at least announced long ago by Goncharov, I think in 2 different papers, but not with a proof, and then eventually published in Goncharov. In the meantime, Terasoma found a very different proof of that, that if we take that as, here I can write that, is true. So the upper bound, so the dimension of zk is less than or equal to that coefficient. There are 2 statements in a sense, less than or equal or greater or equal. Greater or equal is completely hopeless, because that would need some insight into transcendental number theory, which no one seems to have, not in the least at the moment. But the upper bound is given using, so here in terms of algebraic K theory, or mixed-Tate motive, theory of mixed-Tate motives, which is now, I think, rather firmly established, at least for a number field. And Terasoma gave a sort of constructive reduction algorithm, rather complicated. I certainly have not.
And it follows also from Brown, from the result.
From recent, yes. Mm-hmm. Okay. But yeah, I'll get to Brown in a minute. Okay. So, yeah. And the counting arguments with these, this recursion suggests the Hoffman basis conjecture. So, yeah, all multiple zeta values can be written in terms of as linear as in terms of this maybe bad as Q linear combinations of zeta 2 to the A1, 3 to the B1, up to 2 to the AR, 3 to the BR, where, yeah, with AI, BI greater or equal to 0. So only 2s and 3s. So that really looks, I mean, very ad hoc, so you would, not really convincing.
That what I wanted to say, that the previous result is a consequence of my basis function, obviously.
It would be a consequence of this if you could prove it.
Yes.
But we're not there yet. Well, someone made quite some progress on that. But in the meantime, there is... Okay, let me now state the connection. We'll come back to that. Don't worry. A quick GT connection. So just to mention 2 completely different occurrences of multiple zeta values. So the first one, take all these multiple zetas and take them into a power series. Well, power series in two variables, non-commuting variables. So they occur as coefficients. Well, we can define them as the coefficients, obviously. In a generating power series. In two non-commuting variables. An x, y, and then we write it as something like phi of x, y equals 1 plus sum over, take zeta in the notation with zeros and ones, and 1 minus 1, 1 up to 0, and r minus 1, 1, and here you take the same x to the, why do you take minus, makes it even, well, okay. Up to x to the mr minus 1 y.
Replace 0 by x and 1 by y.
Ah, yes,
Yeah.
and 0 corresponds to x and 1 corresponds to y. So you sum over all convergent zetas. I hope that's right. At least roughly that's the idea. If there are minor details, don't ask me, ask experts, because there's so much more about that. And the point is that this phi has occurred before. This is the so-called Drinfeld associator. And I guess Kontsevich at the time was one of the few people who had seen both these rather abstract looking theories of Drinfeld and was closely related to Zagier, who had these experimental data. And he saw that, if you look at this coefficient, the coefficient wasn't given as a zeta value, it was given as an integral. And therefore, it must be like that. I think he bridged the gap at the time. And so the Drinfeld associator occurred sort of in Pierre's talk, at least implicitly. Well, it satisfies, the phi satisfies three famous relations. So, two-term, hexagonal, I think two of them, and this pentagon equation, whatever they, and the conjecture is that the Drinfeld associate is strong enough to see all the multiple zeta relations. The conjecture phi x, y symmetries, I call these symmetries, imply all the MZV relations. And then we have a beautiful result by Ritual saying that
what do you mean by a symmetry behind the relation?
the symmetries are these three relations that I didn't give. So Pierre wrote down the first two. So he wrote, I think, with 1 and 2. And then he had the third one with the pentagon.
Same thing.
Same pentagon. So,
Same five.
well, it's slightly different context, but it's closely related. So,
It's really pro-unipotent pi 1 versus pro-pi 1. So we are in the pro-unipotent context. But the relations are the same.
and for us that suffices. So while Drinfeld needed 3 equations, or 3, one was double, he only needs a single one, which is much nicer. So pentagon should imply all the multiple zeta value relations. And actually he also compared those. Another Foreshore, I mean the same Foreshore, but another result. So one is contained in the other. So I think double shuffle is stronger in a sense. So whenever, so your result DRT lies in DS. what does it say about the relations? So any any relation coming from the Drinfeld associator is already captured by the double shuffles. So double shuffle in a sense is stronger. Yeah, but yeah, that's okay. So he'll talk about this. So I want to understand. I really feel like I'm stupid. So I thought I understood, but I don't see the implication. So what does it say about the relation? So maybe you can tell me.
What do we understand right now? Maybe there's a connection.
Okay, there's a connection. So one is contained in the other.
What? The double
The solution of one system are part of the solution
No,
of
that's
another
what
one.
you written was right. What you written was right.
Yeah, but I didn't make any sense of this. So I want to state it in terms of relations. So if you have a relation, if there's take a double shuffle relation, it's already coming from associator. So
Is that pentagon relation?
sort of, yes, that's it. What it said, but I'm just getting confused here. Okay, and well, that was the first context, and the second context was control of money. That was sort of the connection to operas, because they showed that zeta of A occurs for any A as a period for M0n. In fact, where n is n equals the weight of A minus 3. Okay, it doesn't really matter. But these zetas occur as periods, which means integrals, algebraic integrals against algebraic differential forms. In okay, what do I mean by a period? Integral of an algebraic domain of an algebraic differential form. That's how Cansevic-Xavier call that. I think that's what they call period. And so for instance, think of the circle, unit circle, certainly something algebraic. You take dt over t, that's certainly algebraic as well. This gives us 2 pi I, so that is a period. And so you can form more complicated ones, and MZVs obviously are periods. Okay, so we can talk about periods of these moduli spaces, and they found that any zeta occurs as such, and they conjectured conversely. Converse is true. And then Mattis Brown corroborated this. So he proved that indeed any period that you can find on these moduli spaces is connected to multiple zetas. Now that's operads and multiple zetas, I think, maybe really on the nose. I hope that.
Always the operatic structure is involved?
The M0n's, if you put them all together, like what we've seen in the Grothendieck or in this tower, that for the precise operatic structure, I'll like to, yeah, multiple.
No, not M0n bar.
Again?
M bar, yeah.
Bar, if you do
details, yeah. So there's some notion of modular operad which people will talk about.
You take spheres with points on them, you glue them together, and then when you have this, you glue.
I know the opera structure, but why this opera structure appears at the zeta values level? Where this multiplication appears?
Lost money.
Again, iterated integrals, because Francis Brown simply showed that real points in M0n can be stratified as a union of associahedra. And this gives us these values. This is what he did, essentially. I listed. social hydra is a family of polytopic, it's a operant structure.
The one encoding the A infinity algebra.
Strictly speaking, it's not A infinity because there is a dihedral symmetry, there is involution. It's called kind of a, what is it called, A infinity with this involution for special value.
Okay, and just to finish off, just two more little things to say. And further important structure is a coproduct on model zeta values. This has a beautiful combinatorial way of description given originally by Goncharov, and I learned from a paper of Francis that already implicit in Ihara, maybe a dual version of that. And Francis used that to show, very recently that this Hoffman basis conjecture is true for a certain class, for so-called, well, relativic zetas.
Oh, it implies the ordinarity. The ordinary.
No, it's not. No, it's not a basis. No, it's not a basis.
No.
How do you know it's a basis? They're
No.
They're not random.
No, it's not a basis.
So it's a generating set.
You said.
Yeah, well, certainly they generate. I agree, but okay, you lose a point. The Hoffman basis conjecture is true for these, so it's really a basis there, not just a set of generating set.
Hoffman basis.
Basis conjecture. And this implied an even better result about which he should talk, so-called Ihara conjecture, which says something about certainly algebra generated in odd degree only, and so in a sense, and these odd degree, by a single generator in odd degree, they should correspond to the usual odd zetas. So in that sense, I think one can say that maybe this result says something about the usual zeta values via the big detour of multiple zeta values. And that was roughly the bridge I wanted to give. Yeah, sorry for slightly over time. His fault. Sorry? It's your fault. He said only half an hour late, and I said it's your fault.
You finished early. The one you said you hadn't started.
Oh, okay.
We still have 20 minutes for questions.
Just a comment to complete your story. I mean, there is a new associator, explicit associator, which was constructed by Alexeyev and Tarasyan. It's a conjecture. It's not known. Its coefficients are multi-zetas. It's a conjecture now because it's kind of it's a big problem. But I mean, if the usual associator kind of leads us to conjecture that it will control all the relations, then if one proves that coefficients of this new associator are multi-zetas, we can have a kind of an explicit formula for action of GRT on multi-zetas. Okay, in some sense multi-zetas, not on values. So I will talk about it in my final talk.
Okay, so I think there's work for you to be done. Maybe, yeah, very good, yeah.
Can I ask one question? Have you ever heard the phrase sticky shuffle?
Sticky shuffle?
Yeah. I've heard people do in stochastic analysis do something which they call the sticky shuffle product, which, so far as I can remember, is exactly the same as what you call a stuffle.
Ah.
I can
Shuffle.
Okay.
I think it's the same, but I'd have to look it up.
Well,
You've never heard the term.
it comes from the fact that in the formula is a correction term.
There's a correction term, exactly.
And it
Exactly.
comes from that.
Yeah. I just want to.
No, it is the same.
I think it's the same. My other question, sorry to ask two questions.
It's not.
You remember you wrote down some iterated integrals. Have you looked in Consevich's quantization paper
No.
to see if those
No.
exact
No.
integrals
No.
occur. Because
When-
very similar integrals occur
Uh-huh.
when he writes down an explicit formula for the quantization.
Uh-huh.
Okay? I mean, I
Really
look- I
over
look-
simplex and one forms, so these simple one forms.
What?
Summations are much more complicated.
Well, I look in concept.
I think the thing you mentioned for concept is L infinity equals the isomorphism. This integral, these are not the same kind of integrals. Are integrals of population space or graph. Or
No,
there's some other integrals
It's
there.
a different integral. It was only proven that zeta 3 occurs in some of his ways
Okay.
by Lavoie and Felder.
Okay.
It's the only modular rational zeta 3 does occur as a value, but not others. So his
Okay,
integrals
okay.
are very different from his.
Okay.
But typically when you see zeta 3, then you should see all the
Yeah, but
others.
still, if you look at the paper by Felder and Thomas Lavoie, it's a very complicated integral and graph which gives zeta 3. So it's far from obvious. It's not a simple graph
Mhm.
to guess it is zeta 3. So what are higher values?
Okay.
Okay. Any more questions? Okay, so thank